can you give me an introduction first? Thanks for joining us, everyone. I'll let Dr. Jamal Dean introduce Thomas Thundat today, but we're really excited to have you here virtually to give this talk. Jamal, still there?
Yes, yeah, I'm still
Okay.
here. Are you ready?
Yeah, we're all good to go.
Okay, so good morning, everyone. My name is Jamal Dean. I'm part of SMAP and with the School of Biomedical Engineering and the Department of Electrical and Computer Engineering. Today, it's a great pleasure and honor for me to introduce my good friend, Dr. Thomas Thundat, who is a SUNY, this is the State University of New York Distinguished Professor, and a SUNY Empire Innovation Professor in the Department of Chemical and Biological Engineering at the University of Buffalo, the State University of New York in Buffalo. He's also an honorary distinguished professor at the Indian Institute of Technology in Chennai. Thomas was also in Canada for several years. In fact, he was a Canada Excellence Research Chair Professor at the University of Alberta. Previous to that, he worked at Oak Ridge National Lab, rising to the topmost position as a scientist researcher. He received his PhD in physics from SUNY at Albany, and he's published numerous papers, in fact, over 500 journal papers, 45 book chapters, and he holds 46 US patents. He's an elected fellow of numerous societies, including the American Physical Society, the Electrochemical Society, the American Association for the Advancement of Science, and the American Society of Mechanical Engineers. His research is currently focused on developing new concepts in nanomechanical sensing, energy conversion, electrical energy transmission using a single wire, and novel concepts for charge separation and storage. Most recently, he's gotten into the digital healthcare or healthcare area, and today he's going to be talking to us on enhancing and preserving the quality of life for citizens with assistance need. Thomas, it's all yours now.
Thanks, Jamal, and my apologies for this Microsoft team. I don't use this very often. So let's start with acknowledgement. I have lots of people I work with, it's all here. And so outline for the talk, I will talk about the sensors and need and talk about the micromechanical sensors, and why AI fails in this, try to get the analyte detection done. Then I will address the selectivity, addressing the another problem, challenges in the battery, and how this can be used for societal needs. So if you look at our society, we have number of older people above age 70 or so. It's increasing. In the US, by 2050, will have more than 66 million people over the age of 70. In Japan, 1/3 of the population will be in this group. So the question, these people, as we get older, there will be lots of challenges. And remember that we have also declining birth rate and people migrating to cities. So rural areas are going to have a big problem. And we can see that in the Midwest in the US at this time. So we'll start with the sensors for health. That's what lots of people are interested in, especially elderly people. If you go to doctor's office, basically most of our physical sensing and for example, blood work and things like that take time. And none of the biomarkers are 100% indicative of any disease, right? I mean, we don't have any biomarkers, only partially selective biomarkers. That basically means you have to have array-based sensing. And right now, we don't even use the breath or odor as a disease detection, even though many years ago, hundreds of years ago, or thousands of years ago, people used to use odor as a for disease detection. So most diseases, they have certain characteristic, especially in the breath. If you look at the breath or a skin emission, will be okay too. But it's so many molecules, volatile organic compounds as well as semi-volatile organic compounds. And it's also complicated because the skin also has lots of bacterial colonies and things like that. So the question is that can we use this as a easy way, non-invasive way for detecting diseases, especially for the old people, so they don't have to, if they are living in the villages and so on, they don't have to go to doctors right away if they can find out whether it's a normal or it's a serious case or something like that. So a real-time sensor that can detect multiple analytes. So this is from the Star Trek. They used to have this tricorder, and lots of people are trying to come up with this idea that we can have a portable device that can detect everything practically. So immediate need, so of course, is a healthcare. It has to be non-invasive, breath, urine, or something, or saliva, something that we can easily get. And most of these old people are going to live alone, because children are already gone. So we have to look at the safety, fire, carbon monoxide exposure, all kinds of things like that. And most of these people also have trouble with the daily activities, even plugging in, to the outlet. Some of the devices, electrical devices, is hard for them. We may not realize that, and preparing meals and, or even eating, some of the people may have some issues because of shaking hands and things like that related to diseases, and also moving around. So how can we do something for this? We already have this, sensors, smart, people working on sensors for smart and connected communities. This is already there, and people are working on it. They're coming up with all kinds of sensors for automation, infrastructure monitoring, even healthcare, agriculture. So there are some work going on, and can we take those things and help in this particular case? So what we are working on sensors is a microfabricated, cantilevers. It looks like a diving board, and you can actually use it as a sensor. So the length of these things are around, maybe 100 micron or so. And you can make this into arrays of, hundreds of them. When the molecules sit, some analyte molecule or target molecules come and sit on the sensor, then you can see that the resonance frequency of the cantilever changes, and it's in kilohertz. And if you have some specific, receptors, like a self-assembled monolayers or something, the cantilever also, and assume they are only on one side, that the cantilever is going to bend because of the change in surface energy, which is basically surface tension. So that's also given here. This is how much is the bending. It is related to surface stress and the material properties like the Young's modulus and length and thickness. In addition, we can also make these sensors or cantilevers into extremely sensitive thermometers. So that I will talk about it towards the end. It's one of the best the thermal sensor that works at room temperature without any cooling involved. So these are some of the things that we made over the years. This is a complete packaged system, different versions. And this is a chip. My friend Anja Boysen made this in Denmark. So there are 32 different sensors in this microfluidic little well. They are all electronic readout. so you don't need any optical beam deflection and things like that. So we can make it extremely small. These sensors are based upon capacitive approach, where when they bend, when the capacitance changes. This is a piezoresistive one, this is a piezoelectric one, and so on. So you have lots of freedom in design. So these are physical sensors, and the question is that how do we make them into chemical or biological sensors? So you can make a deposit. So there are 4 cantilevers shown here, around 100 micron or so. You can immobilize some kind of a polymer or self-assembled monolayer, nanoparticles, biomolecules, or things like that, using the inkjet idea. Or we can also use other techniques like self-assembly and things like that too. Of course, these molecules, receptors, or these chemical interfaces should be attached to the surface. So we also have to have some kind of a coupling chemistry to link them. So now I'm going to talk about the selectivity based upon these immobilized receptors. And so first simple example is that you have put a little thin layer of palladium and expose it to hydrogen. Then you can see that the cantilever bends as a function of concentration of the hydrogen. So this is an excellent simple example. This is a response to benzene. Again, this is in parts per million only at this time. You can go even lower, higher sensitivity. So here it's a thin layer of polychloroprene, put it on the surface, very thin layer, and the benzene comes in, interact with the layer, and the cantilever bends. So bending as a function of concentration. And remember that the sensitivity can be improved a lot by geometrical optimization. This is inside the liquid. We have sensing calcium, for example. We have the self-assembled monolayer on one side of the cantilever, and calcium ion comes in, and then they bind and makes the cantilever bend. And this is in a mixture. So if you have potassium, magnesium, sodium, most of the biological fluids have it. So they don't have much response. Calcium has a higher response. But if you increase the concentration higher, they also have some effect. So physiologically relevant concentration, this is okay. And this is a detection of another organophosphate, like the paraxon. We immobilized acetylcholinesterase that they're looking for. Actually, this was developed for agricultural use, but this can also be used for home applications too. And this is another example of array-based sensing. There are 8 cantilevers. We immobilize them with the different antibodies for looking at the exosome. And you can see the cantilever response, and then you can clearly detect antibody-antigen interaction is extremely selective. So this can also work as a biosensor. So the idea is that, okay, for example, vapor detection, you can have one chip with different cantilevers modified with different receptors. For biological thing, it will be a separate chip where it is compatible with the liquid, and we have immobilized with some kind of a bioreceptor. And so the idea is that, okay, can we make a artificial nose? Because we talked about the scent of diseases, breath analysis, right? In a very non-invasive way of doing it. So we are not born with any specific sensors or receptors for particular chemical, like a sensor for pineapple or strawberries. We don't have something like that in our nose. But nose works mostly, or people believe that it's based upon pattern recognition. We have lots of receptors, and then they all bind differently to different chemicals, and then give us a pattern. And we kind of learn that pattern and associate them with the specific, pineapple or apple or orange and so on. We can do similar approach. We can have an array of cantilevers modified with the different receptors, so they all act differently and form a pattern. Then you can use principal component analysis or neural net analysis, advanced machine learning. All these AI technique now perfected to work on this type of data. So this is a little device that we made at Oak Ridge when I was there with Tom Farrell. So this is a little capsule with all the electronics inside it, including a wireless telemetry for 8-channel. This is for blood gases. So, the vapor goes inside it and cantilevers are underneath it. And we implanted in a rat, and then rat is inside here. This cage, it transmits the data. There's an antenna here, and it picks up the signal, blood gases, and it works perfectly well. Only problem, we had to stop this project because it works with the 2 hearing aid batteries going between these 2 clips is somewhere here, and the battery, dies after transmitting data for a while. So you had to cut open the rat again, change the batteries and so on. That is not very good. So we basically stopped the project and didn't continue because we didn't know how to overcome that issue. So sensor challenges, I didn't tell you that the lots of these receptors, they don't work very well, especially in complex mixtures. If it is only one type of gas or mixture of 2 or even 3, it may work. But if you have a complex mixture in like a real world applications, it doesn't work. It gives a false positives all the time. And so the selectivity is a problem. Another problem is that reproducibility from sensor to sensor, because this immobilization step, chemical, it involves multiple steps, and so the probability of error is high. So sensor to sensor variation is huge, very irreproducible results. And the batteries is another problem. And sometimes the detection time is also a problem because the molecules are coming by in diffusion. But how do we solve this problem? So if we can have a orthogonal sensing, we can get rid of the selectivity challenge, and animals use that type of idea. So we can also look at the different type of signals. That's what I'm going to talk about it. So when we develop the selective coating, we always make sure that it is a room temperature reversible detection. So the target molecules come and bind to the receptor, and when you remove the molecules, the ambient, decrease the concentration, they come out. So it's in thermodynamic equilibrium. We can go high selectivity, make it more. It doesn't dissolve like a covalent bond or Bronsted acid base approach and things like that. In that case, it doesn't reverse. It is so high selectivity is there, but not reversible. The simple idea that physisorption or low energy interaction, room temperature reversible, and everything bind with it, that it's hydrogen bonding or van der Waals interaction. So everything in the air binds with that. So the selectivity, we lose the selectivity. So that is a big problem. So we thought maybe if we use array based, like I said earlier. So all these 32 different cantilevers are modified with different self-assembled monolayers or polymers. And I'm showing only 4 of them here, A, B, C, D. Actually, there are 32 of them. And we expose it to, say, acetone to training purpose. And then this is a response from the array. Then we expose it to ethanol, you get another pattern, water, TNT, water molecules in vapor, and toluene, and unknown vapor. And the idea is you say, oh, we can use a principal component analysis or neural net analysis, try to figure it out what it is, right? So we found out that it doesn't really work, It works only when mixtures are simple, 2, 3, and things like that. In a real world condition where there are so many, it doesn't work because everything binds with this room temperature reversible hydrogen bonding or van der Waals interaction. Another one is that even though we put the immobilized with the selective receptors, the receptors don't go uniformly. There are always non-uniformity, and because since this immobilization process involves multiple steps, the probability of error is also very high. So sensor to sensor reproducibility was the biggest challenge in using this machine learning approach. So how to overcome this problem? Maybe we have to go to clean room and then do the chemistry there, or come up with a better technique, or we can use different type of ideas. So this is what Einstein said. We can't solve the problem, today's problem with today's technology. We have to think about something different. And the Feynman said, if you can think about it, you can make it. So one of the ideas is that maybe we can use a photothermal cantilever deflection. So I told you earlier that cantilevers are extremely sensitive to temperature, and so delta T and the bending of the cantilever is directly related. Even is Young's modulus of the bimaterial cantilever. You have to make the cantilever bimetallic, bimaterial. You put a thin layer of aluminum or gold. So Young's modulus and coefficient of thermal expansion of the first element, and this is the second element. So, and their difference, makes the cantilever, a sensitive sensor for temperature. And as you know that the thermal mass of this or thermal capacitance of these cantilevers are extremely small, very small mass, nanogram mass. We can even make it even smaller if you like. So they respond very fast, and we don't need any receptors in this case. So we can allow the molecules absorb on the surface, adsorb. They're just sitting there, physisorbed. And what you do is that you expose it to light, infrared light. So that's what is shown here. So here is the cantilever bimetallic. We take infrared light, focus it on here, and you tune this infrared light from one wavelength to another wavelength. So if these molecules are absorbing the light, photons, they get excited, and then when they de-excite, they produce some heat. They're called non-radiative decay, and that is enough to make the cantilever bend. So if you look at the cantilever bending as a function of wavelength, you see the spectrum. Let me show you an example. I'll skip this one. So mid-infrared rays, that's where the most, what do you call the molecular fingerprint regime. So these are the most important part of the infrared spectrum for molecular identification. All the molecular groups have very unique, spectral absorption characteristic there. So you hit it, the molecules are sitting on the cantilever, you hit them with this light, they get excited, non-radiative decay happens, cantilever bend. So I'll start with, even though this is explosive, but we can use any molecules you want, then I happen to have this result. So This is TNT molecules absorbed on the cantilever. You are exposing it to 2 micron to 14 micron wavelength of infrared radiation. And suddenly you have, you're plotting the bending as a function of wavelength, you see the spectrum. This is PETN, another explosive on the same cantilever. So this is physisorbed and they will desorb after some time. And you can get the spectrum of PETN. Now you send the two mixtures of these two vapors, and you see the a linear combination of these two spectrum, TNT and PETN. So we know that these molecular vibrations are independent of each other. And if you get a spectrum here, and you already know the spectrums of other molecules, you can use machine learning to figure it out what it is. So this is a more complex mixture or chemical called naphtha. It's like a kerosene absorbed from the cantilever. And the top one is the cantilever data. And you can see this is a picogram amount of material absorbed. Picogram is a trillionth of a gram. And this is the standard one, ATR and FTIR. These are big equipment, very expensive, very sophisticated light source and so on. This is just a glow bar and a filter wheel, so it's a very small system, and it gives a nice spectrum too. Here you need a milligram amount of material, you need lots of material for here, but here you have picogram amount and it gives a spectrum. Remember that these spectrums are photons based upon the Beer-Lambert's principle. You hit it with photon and you detect the photon coming back, or what is not so absorbed by the target molecule. In this case, we are looking at the complementary process, the heat involved. So these two spectrums, they may balance, match at the energy level, at the what wavelength that is happening, but the peak ratios may not match because this is a complementary process to this. So this is a more rich and direct method. This is heptane, again showing the cantilever data with ATR and FTIR. We can identify all the molecular vibration. This is octane, and I can go on with all kinds of things like this. Even detect methane, CH4. Methane is a symmetric molecule and it doesn't have a chemical handle. And also it doesn't absorb on the surface, but it absorbs a nanosecond also, what you call the residence time, you can calculate. But that is enough for us to get a spectrum, and we have seen that the molecules, physisorbed methane molecule is around 10 to the power minus 18 gram oxide. So key advantage of this idea is that you don't need polymers or self-assembled, but you don't need any receptors at all. You have just a cantilever, coated with a metal, that's it. And very powerful technique. And it gives all kinds of spectrums, even if there's a combination of molecules or complex mixtures, you get a forest of peaks. But if you know what you're looking for, you can analyze the data to get it. So this produces a huge amount of data. So the question is, what about liquids? We can do liquids too. So this cantilever, this is a cantilever, little longer, 500 micron also long. We can make a little microfluidic channel on the top of it and send the liquid through this. So the total volume here is around 50 picoliters. And now you can shine different wavelengths and they get hot. Remember that this cantilever is bimetallic, so they will bend. So you can get the chemical composition. And by just looking at the resonance frequency, you can find out the density, since volume is is already known. You can also get the viscosity. And if you hit it with a sudden pulse of light or something, you can also look at the thermal properties of the liquid. So this opens up a multiple different signal coming at the same time. This is an example of a amphisilin salt inside the cantilever, and this matches perfectly well with the FTIR data. This is fumarate data and glucose spectrum. Again, cantilever bending as a function of wavelength. Remember that this is only 50 picoliters. This is a physiologically relevant concentration. So rest of the time, I'm going to talk about the battery challenges. So this is a sensing, and we can use it. Produces lots of different data. So we can, on this data, orthogonal, the spectroscopic data, and if you use the receptors, even though it doesn't work in the complex cases, but the spectroscopic data can augment the other data, making it much more reliable. So the question I said earlier, we stopped the program because of the battery. So how do you overcome this battery problem? So we have been told that we need 2 wires for electricity transmission, and 1 wire for the electron to go and another wire to come back home, right? Electrons need to go home. But Tesla, this is Nikola Tesla, 100 years ago, shown that you don't need it. You can actually transmit electricity through 1 wire. And so this is a different concept, and I'm going to show you that. So if you have a wire, you can create a standing wave on it. Even though we learned that standing wave don't carry energy, we can actually use that standing wave basically to power things by making the load part of the circuit. So this is the 1 wire, and it's a quarter standing wave. That's this purple thing you see is the quarter standing wave. These are the Poynting's vectors as you continue. So here, but actually it should only half of, quarter of them should be there. The whole wave is little longer. This is just to show that how it works. So this is a energy go back and forth. So this is actually it's done in Albert. We have the similar setup here too. This is a linoleum floor, rubber bucket, wooden piece of wood, and a copper wire, and a light bulb. This is a little piece of metal to provide a little capacitance to reflect the light and the wave through that is coming through this wire. And you can see the light bulb is on. And this is a video I want to show you. So here is a wooden desk, and this is a 50-watt light bulb or so. And this is a 1 wire coming out of our power supply. And you can touch it, nothing happens to you. You can put it there, light comes on. And as long as it's touching the aluminum foil, power comes on. And you can touch it, and you don't get electrocuted. So this is the way it works. So this is aluminum foil. This is the wire connecting to it. We put this coil into 2 parts, and load is in parallel to one of the coil, and there is a stray capacitance, and this model we have published already, and it works. And this is a little bit more complicated math. The only thing I wanted to show here is that in the standing wave, the E and H vector, they are out of phase in space and in time. This is the another example, again wire, the metal desk with a formica top, which is an insulator. So it will work even with a thin insulator. It can go through it, and it's perfectly safe. This is a toy you can buy from Walmart. We removed all the batteries, connected the motor by wires to the leg, and this is a rubber, made out of rubber, and this aluminum foil, 1 wire. And so we are going to put it on the top of it, and it will be moving around. So as long as it's on the aluminum foil, it gets the power. And here you have two of them, and you can also communicate them through the power supply. So the power contains the information to so they can talk to each other. Also, they can also communicate with us. We can communicate with them. So this is another one. If you don't believe, this is a motor, a stick, and a LED, and connecting to this coil. And remember that it's only one wire, and you can see that it started vibrating, and the light is LED light is also on. So you don't need two wires. That's what I'm trying to say. This is a cell phone charger. These are copper sheets, basically. We cut this thing across, to avoid any eddy current losses, so you can increase the efficiency. So put it on the cell phone, there it comes on. And remember that this copper sheet can be as big as the football field if you want. It still will work. So this is our important for if you want to help older people. They can have their devices, toothbrush or the shaver, and all those things can be charged. So you don't have to plug it in. Like I said earlier, plugging it is hard for lots of people. Or even their spoons and fork which can be stabilized with electronics, and that can be charged. So there you don't have to charge it independently, because most of the houses have only limited number of outlets. Here you can put all kinds of devices on it. So we can think of a different type of houses. This is a Christmas tree light showing the same idea again. And coming back to having the sensors on the person or inside the person. So you can have lots of sensors. Remember that I showed you earlier that the battery is a problem with the sensors, especially if it is implanted. Now imagine you have the battery on a belt or your watch or something like that, and you can power all the sensors on your body, around the body or inside the body. So you can have even implanted sensors. So you can power come from outside. So this is Charles Van Ness. Now he's a professor in Tennessee, and he connected the power to his hand, and the power comes on his shoulder, his head, other hand. So you can have lots of power anywhere you want, and it is completely safe because current and voltage are out of phase. So there's no real power unless the power comes inside the coil and it changes the phase. You can also design the house in such a way, especially for older people, so you can have you don't have to carry, you don't have to wire anything. The power basically come out of the underneath the carpet or from wall or something like that. You can think of sheetrocks with some aluminum foil behind it, and so you have a powered wall basically. So you can just keep your TV or devices on the wall. We also did Tesla. Nikola Tesla wanted to do he had a dream that he can power the whole world, and this can be useful for all kind of applications, for powering the village or something like that. Of course, it's a dream. So we wanted to do that, so Tesla actually drilled a hole and then made a tower in Long Island, and we didn't have we couldn't drill a hole. So we found in Alberta, Edmonton, we found a house with a very sharp, or a steep backyard, so we went and talked to them and see whether we can run an experiment. So we did the Tesla experiment here. So the whole yard is now powered. Only thing you need is a little coil and just touch the ground. That's what is showing here. There's a coil, and we use only low power because We didn't want people to worry about the earthworms and bugs and so on. You can see that the one wire is touching and the other wire is on the coil, and the LED comes on right away. And right now we have a NSF project. We are doing this for agricultural sensing. So you can actually implant the sensors underground and then look for the soil health. That experiments are right now underway. So we also remember when we talk about old people, their mobility is an issue. So we found a scooter, and again, charging is kind of hard. So we basically, let's say, so this is the aluminum foil put on the floor and powered with a single wire. This is my student Rebecca. So this is not touching. Nothing is touching the aluminum foil. And it is picking up the power from the road, around 1.7 amperes and so going to the using and so we were able to put something like a 36 watt. That's what for this scooter, and we have shown up to 200 watts. So we even put this on the road. We thought, okay, we put aluminum foil on the road. Of course, we didn't have a long aluminum foil, so it's a short distance. And then Arindam Fani, my postdoc, is riding the scooter, and the power comes from so basically this we can design for old people for their mobility. This type of houses and things like that, so they don't have to charge things or connect things, or everything is automatically charged. So you may ask, what about the health effects? So we looked into it, and all the the power that we are radiating is consistent with the much lower than the Canadian and US standards. So in summary, nano mechanical sensing coupled with the photothermal spectroscopy, and it can generate a big data, and then if using the machine learning technique, we will be able to even use the breath analysis and things like that for monitoring health and the safety of the home of older people. I didn't talk about the pre-concentrator. I kind of skipped it, to improve the detection, sensitivity, because sometimes the chemicals are much lower concentration than you can think of. For example, the PFAS. PFAS is everywhere. It's in the carpet. It's in even the drinking water. And so the concentration is around parts per trillion. So it's kind of you need a pre-concentrator. So I didn't talk about that, because you want to do a fast detection. You want to have this molecule come and sit on your sensor. So climate is changing, society is changing, so we have to adapt. So this is a quote from Charles Darwin, saying that the only way to survive is by adapting to the we cannot change the global warming, so how do we adapt to it? So, and especially when the population is getting older. So I will stop my talk here, so that I went too fast in many places, but we can have some discussion. I'll be happy to answer any questions that you may have.
Excellent. Thank you so much for that amazing talk. Lots of questions. We'll put it out to the group here if anybody has any initial questions that they want to get things started on. I can kind of throw a broad question out there as people are organizing and formulating thoughts. But as I said, really interesting stuff, wide spectrum of technology. And I'm curious on your sort of approach to this, because you cover things from, you know, the sensors and the cantilever all the way to the power supply. And I guess my question is, how do you kind of approach that with respect to designing technology and then to integrating that with end users, from like finding a problem to finding that technology?
Yeah, that's a very good question. So right now, of course, everything is connected by the funding, right? I mean, how do you approach the problem? Right now, we have funding for, this agricultural sensing, not for anything for the health or of the people and breath analysis and things like that. But the same platform can be used anywhere, So if you develop somewhere, that's what I showed one slide, is this connected community, IoT. It's already existing, so people have done lots. So basically bringing all those things together and understanding the problem, because if you look at the IoT and the present sensing, all based upon physical sensing, it's easy to, because even AI technique is basically all based upon cameras and sound, and which are well, primary, our senses, and cameras are so developed, I mean, you can get very high resolution images, and using that to, but when it comes to chemicals, the molecules, even a room, where I'm sitting right now, there are 7,000 different molecules floating around, so the enormous number of molecules. So how do you do a varying concentration? And remember that water molecules are appearing, parts per thousand, and they have a huge dipole moment, So the chemistry, as we think, will run into lots of interference. So the question is that how do we bring orthogonal techniques so that we can, you will get a response, huge response, and from there, how do we extract the signal out? So breath is a good one. So we are trying to get funding for that too, and so it's all based upon what the funding agencies are looking for at this time, right? So, and the battery challenge, lots of people don't address that part, So people are working on batteries too. So of course we have to work on both sides, and see which one is going to work out, because I focused here because lots of old people and living in older homes, the number of outlets are very limited. Even plugging in basically a device in the outlet is extremely hard for older people. So we come up with this type of idea where they can put everything on the top of it, and then they're just powering it.
Yeah, it's again, I think it's amazing to see all of the different like applications that you have, but also just like the opportunity for all those things to impact in so many different ways. It's exciting. Oh, and you can probably, I think your screen's still sharing. You can probably hit stop share if you want it. We'll pass it to the audience then. Is there any questions that people have out there? You can raise your hand, or you can just turn your camera and your mic on. I know one of the other things was so you had the single wire coming through the body with the sensors on. I think that kind of probably resonates with a lot of people here. what's the, the capability of that in terms of how much power can that generate in a sense? Like you had some LEDs and things on, but what kind of things could you power in that context?
I think we haven't done experiment with the higher power because it will involve IRBs, and unless there's a huge effort into it, it will be hard. So we were just basically demonstrating that it's possible, and looking at the health effects and things like that. We said that there is no real power, right? It's a reactive power. So current and voltage are out of phase. So it is completely safe. So your body is already powered, and so you have whether implanted sensor inside you or on your shirt or on your body or wearing it, it will all power, and it's completely safe. That's what I wanted to emphasize, because current and voltage are out of phase, and most of the time people don't realize that there is a reactive power out there.
Yeah, I mean, it's very very innovative stuff. It's very new to me as well. So we're quiet today on the Friday. Any questions out there from anyone? I have a lot of questions. I don't want to kind of
Please,
dominate.
I will be happy to answer it.
So I guess maybe one more from my side. You talked initially about, some of the funding opportunities dictating some of that. There's also, a lot of patents that you've been involved in. And I'm curious how industry kind of comes into play in this. Like, how much do you have companies like Tesla or all these sensor companies that are looking at the technology, and does that drive some of your work, or are you very on the publicly funded side?
So that's a good question. When I was in Alberta, I went to Samsung and a couple of different companies, including Intel, but I was a little late. That's what they told me, because they already invested in the coil technology.
Oh yeah.
Of magnetic induction, which is very inefficient actually. Because the coil has to be is a dipole, so it has to be exactly along the axis.
Yeah.
Even a slight change, but industry, once they invested some money, they are not going to change it's like trying to change the direction of an aircraft carrier, right?
Yeah.
It will take time, So we were a little late with the technology, So that's what all the people said. But I believe that more opportunities will come up, rather than just using it for powering a cell phone or something, maybe agriculture or somewhere else. That
Yeah.
opportunities industry, it will come naturally after some time.
Yeah, I think so. And I mean, it kind of leads me maybe to another question I have, but I'll see if give anybody else a chance. Is there questions out there? Jamal, I see your mic's off.
I was going to ask Thomas what sort of current levels he's experimented with.
So we have gone up to a couple of amperes, So maximum we have gone is at 300 watts, And
do you think there may be a limit in how far you can go?
I don't know that, because Nikola Tesla believed that he can power the whole world. So we actually made a tower in Edmonton, which is 14-foot tall coil, huge. And unfortunately, there was some design issues, because we wanted to move it around. So we put it on the top of a trailer, which is made out of iron, right, metal. So that interfered with the total capacitance, and then the efficiency came down a lot. So we were able to transmit power through the ground, but it basically changed only the, very, very little power because of this trailer was causing issues, you know. But the one I showed you in the earlier with when we went to a house and then did experiment in their yard, that was only, you know, I mean, just powering 20 watt or something maximum, you know, because people were also afraid what type of damage we are going to do to the earthworms and bugs who live in the ground. But you know, as I said, there is a reactive power, so people, you know, kind of concerned. So that's why we lowered the power. You know, of course, more experiments need to be done.
And do you think it depends on the type of surface you're transmitting the power?
A good question. Actually, you know, in India, in Australia, and places like that, they power certain, say, fence or something like that using single wire, you know, and then they, you know, one light bulb to another light bulb to another light bulb, like in a series, and then they ground the other end to the ground. So return is through the ground, you know, and it works. And they have found out that the longer the distance, the Earth's resistance decreases. So it's kind of, you know, if you look at the resistance, is a rho L by A, you know, when you look at the bigger scale, you know, the area scales with L square, so it becomes rho by L. You know, this is very naively simplistic term. So resistance will decrease as a function of, you know, distance, you know, because the field lines will be spreading out, you know, for the right conductor. And maybe this was what Tesla was thinking. You know, we don't know what he was thinking because he never published a paper. So he thought that the whole world can be powered, and we have shown that, yeah. And the experience from people from India and Australia shows that, you know, the return line, the longer the distance, the resistance of the ground decreases. I was surprised too.
That's amazing.
Actually, I'm surprised because the L and the A are in different aspects. So the L is the physical length, but the A is the cross-section over which you're carrying the current.
Yeah. So if you consider Earth as a cylinder or something like that, you know, so one end to the other end, you know, so L and, you know, the radius now, right? So basically rho will decrease, I mean, rho by L actually, the resistance, right? You know, it's a simple, naive physics, you know, just a order of magnitude type thinking.
And did you do any experiments in different seasons, like fall, winter, summer, and spring?
Winter in Edmonton was too cold to go outside. But we did mostly in summer, you know, this experiment, you know. So if, you know, the has a, you know, the dirt has a different layers, right? And the if you look at the resistance and the short distances, they are very, you know, very, you know, resistive. But once you go larger and larger, this it is more conducting. You know, if you look at our lots of power stations and so on, you know, they ground their return, right? Lots of grounding involved. You know? So it's itself is a very, very, you know, what do you call, complex area.
Yeah, it's really interesting stuff, and I think it's we can kind of wrap it up there just based on time, but I think it's a very you know, inspirational and exciting area to focus on, because I think it shows, you know, as technology changes, we can also look back, and I think there's a lot of things that now once we're old, become new again, and we probably have a lot more hidden advancements and things out there. So Amazing. Thank you for the talk, for joining us. Any last words or anything, Thomas or Jamal?
I was thinking about it, and I think part of the issue may be perception of the public. So have you thought about including some social scientists in your work who may be better at changing public perceptions? Because you know, when you talk to the ordinary person, not necessarily ordinary person, including educated people, very educated people, they're saying, but you're transmitting a lot of power. Power is made up of current and voltage. If the current is high, it can cause some biological effects in my body, etc.
Yeah, that's a good question too. We never thought about including social scientists when we were in Canada. Only when we came to US, only we realized that there's a push towards having social scientists in the so now we are aware of it. Before that, we were not aware of it.
You should have come to McMaster earlier. We have an integrated approach to these kinds of research, where we include people from several faculties.
Definitely, we need everybody, right? So the perception is very important. You're absolutely right.
But you know, there may also be an opportunity to create disruptive companies. So established companies are already well invested in existing technologies. So this is a good chance for really creating a disruption. And maybe countries that are not big in wireless energy transfer would be one place to look at.
Yeah, that's a good idea in third world countries where you don't have to run power line or something like that.
But you can do the same thing that happened with cell phones, right? Smartphones. Yeah. So the wired telephone is well established in the developed world, but developed world in cell phone technology, and it's much cheaper. So, for example, in India, it's much cheaper
cell phones
than in Canada or the US.
Thanks.
All right. Well, again, thank you, Thomas, for joining us. It was great to hear your talk. And if anyone has any questions or things after this, I'm sure they can reach out to you after that. But otherwise, thank you so much for joining us.
Thanks.
Yeah,
all right.
Thanks. See you later.
Bye.
Yeah.
Bye.